Welcome to the Deep Dive, the place where we take complicated stacks of research, break them down, and give you the essential nuggets of knowledge you need to be completely up to speed on the world's most fascinating frontiers.
And today, we're talking about a frontier that sounds like, well, pure science fiction, resurrection biology.
Right, the whole field of de-extinction or species revivalism.
Exactly. The process of actively generating an organism that either closely resembles or, incredibly, is an organism that was lost to time.
Okay, so let's unpack this. We've received a really comprehensive set of sources here. They detail the cutting-edge science, the profound ethical debates, all the specific projects that are ongoing, and crucially, the genuine, proven successes happening right now.
It's really not a thought experiment anymore, is it?
Not at all. It's an engineering challenge.
And the science is moving incredibly fast. So our mission for this deep dive is to guide you through the three main technological pathways being used to achieve this revival.
And then weigh the benefits against the very serious ecological and ethical risks.
Right. And then we'll zoom in on the absolutely surprising list of target candidates, which range from the woolly mammoth all the way to ancient date palms.
And as we move through this, there's one critical distinction you need to keep firmly in mind. When we talk about bringing back an extinct species, we're really looking at three major methods.
Cloning, genome editing, and selective breeding.
We're back reading, yeah.
And the tension here really is between genetic purity and, let's call it, ecological function. Only one of those methods, cloning, has the potential to produce an animal with the exact original genetic identity.
The others, genome editing and backbreeding, they're creating something different.
By their very nature, they're creating hybrids or proxies, so they're built to fulfill the role of the extinct species, but they are not the extinct species itself.
That purity versus proxy debate really defines the entire field. The conversation starts now. Let's jump into section 1. The pathways to revival how extinction is reversed. So when you think about resurrection, I think the default image for most people is Jurassic Park. And that relies on the most direct, but also the most fundamentally constrained method, somatic cell nuclear transfer, or SCNT.
What we just call cloning.
Right. So walk us through the technical mechanism here, and maybe more importantly, its massive limitations.
Okay, so SCNT requires a near-perfect starting point. The mechanism involves taking the nucleus.
The genetic blueprint.
The genetic blueprint, exactly. You extract that from a preserved, viable cell of the extinct species. This nucleus is then put into an egg cell that's been denucleated.
Meaning its original DNA has been scooped out?
Carefully removed, yes. And that egg usually comes from the closest living relative.
So you're essentially taking the full instruction manual of, say, the Pyrenean ibex, and you're inserting it into the operational vehicle, the egg cell of a domestic goat.
That analogy holds up on the surface, but the biological reality is just terrifyingly complex.
Yeah.
Because even though the nuclear DNA is from the extinct species,
Right.
the resulting organism is still relying on the machinery of that host egg cell. Specifically, the mitochondrial DNA, the mtDNA, which governs energy production.
And a mismatch there can be catastrophic.
It can cause profound, sometimes very subtle biological failures.
And that biological failure leads directly to the core constraint you mentioned, the quality of the source material.
Absolutely. SCNT demands well-preserved, viable donor cells, and usually only find those in recently extinct species, things we can cryopreserve or get to shortly after death.
For anything that died thousands of years ago, like a mammoth.
The cellular structure is just too degraded. The DNA might be there in fragments, but the full functional cell is long gone.
We have that one famous, really heartbreaking anecdote that proves both the potential and the profound difficulty of this method.
The Pyrenean ibex, the bucardo.
The bucardo, yeah.
It really is a technological landmark. The last female ibex, her name was Celia, died in 2000. Scientists preserved tissue cultures from her ear.
And in 2003, they did it. They used a denucleated goat egg and a goat surrogate mother, and they successfully achieved the birth of a clone.
It was a moment of pure triumph for resurrection biology.
But the triumph lasted, what, 7 minutes?
Just minutes. The clone died shortly after birth because of severe lung defects. This single fleeting success, it underscores two things for you, the listener.
Okay.
First, the incredible technological feat of SCNT in this context, and second, the profound downstream biological challenges. It just shows that having the DNA isn't enough. if the cellular machinery can't handle that ancient blueprint.
And if we look back at the history of cloning in general, we see similar problems, right? I mean, Dolly the sheep, born in 96.
She had health issues that looked a lot like premature aging.
Exactly. The epigenetic factor, so the way genes are expressed, it seems incredibly fragile when you try to force a regular body cell to, restart the clock of an embryo.
That's the nuance we miss when we just talk about DNA sequencing. Cloning is this delicate operation where the consequences of even minor errors can manifest as severe health defects and short lifespans.
So it's a high-risk, high-reward approach.
And it's really only suited for very recently extinct species where that time gap is minimal.
Okay, so if SCNT needs pristine source material, what happens when the tissue is, say, 40,000 years old, totally degraded and fragmented?
Then we shift completely into the realm of genome editing, specifically using technologies like CRISPR-Cas9.
This is the pathway that's unlocked the kind of iconic ancient species.
It has, because genome editing doesn't rely on a viable extinct cell. It only relies on the information inside that fragmented DNA.
Okay, so for those of us who hear CRISPR-Cas9 and know it's powerful but need the details, the sources mention it started as a bacterial immune system. How does that become our main tool for editing a mammoth?
It's a beautifully elegant adaptation. In bacteria, this system, it defends against viruses. You have a Cas9 protein, which is like a pair of molecular scissors, and it's guided by a little piece of RNA. This guide RNA is programmed to find a very specific sequence of viral DNA. When it finds it, Cas9 cuts it, neutralizes the threat.
So scientists just hijacked that system?
Completely. They simply design a guide RNA to find the target sequence they want to edit, say, the gene for short hair in an elephant, and then they can replace it with the sequence they found in the mammoth genome.
That specific programmability sounds like you've unlocked the cheat codes for evolution. It must be so much faster and more accurate than older methods.
It is transformative.
Yeah.
Because we can now assemble the full genome of extinct organisms from degraded tissues, we can identify those specific adaptive traits.
Which means we can go after a much wider array of species.
Exactly. We don't need a living cell, just the readable blueprint.
So going back to the woolly mammoth example, you can read the genetic code for, let's say, cold-resistant blood, extract that specific sequence, and use CRISPR to splice it into the germ cells of an Asian elephant.
That is the core of George Church's work. They are surgically introducing those key adaptations: long hair, subcutaneous fat, specialized hemoglobin for the cold into the living relative.
But the vital takeaway here is the result is not a pure mammoth.
It is fundamentally a hybrid, or a proxy. You are not reconstructing the full 40,000-year-old genome. You are only making targeted modifications to the modern Asian elephant genome to sort of approximate the extinct species function.
Which means if the resurrected mammoth fails to behave like a true mammoth, if the crucial behavioral genes weren't part of the edit, then the whole premise of ecosystem restoration is undermined.
That is the key insight. The creature you get fulfills a physical role, but it carries the intrinsic behaviors of the elephant. If we miss essential genes for migration or mating or social structure, the proxy might not survive, or it might just fail to do its job.
Okay, let's move to the third pathway, which is less about the lab and more about time and observation. Backbreeding and iterative evolution.
Backbreeding is, you could call it low-tech de-extinction. It's just artificial selection applied in reverse. You select for ancestral traits that still exist in a population, even if they're rare.
So no fancy genetic reconstruction needed.
Not at all.
This is purely about getting a physical lookalike, a phenotype. The aurochs is the textbook example here.
Correct. The aurochs was this massive wild ancestor of all modern cattle, and it went extinct in 1627. Projects like the Toros program are using selective breeding.
So they're crossing primitive cattle breeds that still have some of those ancient traits?
Right. And they're slowly, iteratively trying to achieve an animal that physically looks and acts a lot like the extinct aurochs.
But while the physical appearance might be restored, the genome is clearly different, and you have to wonder if the behavior is really the same.
Absolutely. The genome will be different, and the new animal might lack the original's full spectrum of behaviors, like its deep instinctual fear of humans. It's a functional mimic, not a genetic revival.
Now, compare that deliberate human intervention to this astonishing phenomenon the sources call nature's de-extinction.
Iterative evolution.
Iterative evolution.
This is where nature just hits the redo button completely on its own. It's when a species goes extinct and then a close relative evolves into an almost physically identical creature to the one that vanished.
The story of the Aldabra rail is perfect for this.
It's one of nature's most compelling miracles. The Aldabra rail was a flightless bird that disappeared about 136,000 years ago when its island was submerged by rising sea levels.
Okay.
Fast forward 36,000 years, sea levels drop, the island resurfaces, and is colonized by a flighted rail. Over time, that new population evolves into a flightless species that's physically identical to the one that perished.
The same bird evolved twice, separated by a global catastrophe.
That's why scientists use the term Elvis taxon. The original is truly gone, and the new one is just a very convincing, ecologically functional cover version.
It's proof that sometimes the ecological niche is just so strong that the same answer emerges over and over.
Right, but it's completely unpredictable. You can't rely on it for urgent conservation.
So finally, before we weigh the pros and cons, let's quickly touch on how these tools are applied to plants and also to species that are only functionally extinct.
Right, plant material generally conserves far better than animal tissue. So scientists can use herbarium specimens that contain viable seeds.
Like the 2,000-year-old date palm we'll get to later.
Exactly. Or they can use something called micropropagation, which is coaxing barely alive embryos back to life. If the seed is viable, the resulting plant is a genetic clone of the historical one. Botanical de-extinction is, weirdly, the easiest path.
And for species suffering from functional extinction, so they're alive, but they can't reproduce on their own.
This is where all the R&D from cloning and genome editing pays off immediately. We use in vitro fertilization, IVF, and artificial insemination to preserve these critically bottlenecked species.
Let's pivot to the rhinos for a second. There are only 2 northern white rhino females left. So how is this de-extinction tech being used to save a species that's still technically alive?
The biorescue team is using preserved sperm from the deceased males, collected long ago, and they're combining it with egg cells collected from the remaining females to create viable embryos.
It's an incredible effort.
It is. The plan is to implant these embryos into surrogate southern white rhinos. This isn't bringing back the dead, but it's using the technology designed for the dead to save the living.
That level of sophistication forces us to ask the big question. If the biological challenge of cloning the ibex led to its immediate death, are we prepared for the much larger ethical and ecological challenge of reintroduction?
That's the core of the debate.
Let's turn now to Section 2, weighing the scale, pros, and cons of reintroduction. We'll start with the upside, scientific and conservation leaps.
The scientific potential is truly immense. I mean, the most immediate benefit is just technological advancement. The R&D needed to sequence an ancient genome or perfect a surrogate mother technique for a mammoth creates breakthroughs that are immediately repurposed for currently endangered species.
That is the most compelling argument for me. If you perfect a complicated embryo transfer process for a silacine hybrid, you can immediately apply that exact same technique to help the critically endangered vaquita or the Sumatran rhino.
Precisely. The genetic technologies advanced for de-extinction act as a kind of, a technological rising tide. It lifts all conservation boats.
And beyond the lab, the optimistic claims are all about ecosystem repair and rewilding. The idea that the returned species can act as a natural machine to reverse environmental damage.
This hypothesis centers almost entirely on the woolly mammoth and its potential role in the Arctic. The argument, heavily championed by George Church, is that reintroducing mammoth-elephant hybrids could fundamentally restructure the tundra ecosystem.
Okay, but this is highly theoretical, right? What is the supposed mechanism for reversing climate damage?
The theory involves 3 main actions. First, the mammoths would graze on dead, insulating grass, which lets spring growth emerge faster.
Okay.
Second, their habit of felling trees and breaking up topsoil would expose the permafrost to more cold winter air, slowing the thaw.
Which would slow the release of trapped greenhouse gases.
That's the theory. So it's not just about bringing back a cool animal. It's about restoring a functional ancient ecosystem, maybe even turning the Arctic back into a grassland.
The audacious goal of the Pleistocene Park Initiative.
Exactly. And on top of that, the sheer charisma of these revived species gives them what's called flagship status.
Ah, the fundraising argument.
Right. Flagship species, like a resurrected dodo, would generate massive public enthusiasm, huge media coverage, and most importantly, money for conservation.
So you could leverage that excitement to raise funds for, say, all of Mauritius's other endangered species.
That's the hope. And finally, there is that powerful ethical argument. Humanity, through our actions, drove species like the dodo and the thylacine to extinction. So we have an ethical obligation to use our science to repair that damage.
That sense of moral accountability is a powerful driver. But this is only one side of the ledger. We have to flip the coin now and look at the downside. the serious ecological and ethical pitfalls.
And this is where it gets really tricky.
I think the most immediate concern for ecologists is the risk of creating a new invasive species.
That risk is very real, and it's often understated. If a species has been gone for centuries, its original ecological niche has probably been filled by something else.
So when you reintroduce the long-gone animal, it could just become hyper-competitive.
It could lead to a scramble for resources and potentially cause the extinction of other existing species.
Or if you bring back a predator, you might just decimate a prey species that hasn't seen that kind of pressure in thousands of years.
The ecosystem is a finely balanced system. Reintroduction carries an enormous risk of destabilizing the whole thing, which leads to the environment mismatch problem.
Meaning if the habitat is changed drastically due to logging or climate change, the reintroduced species may just not survive at all.
Not only that, but they might lack immunity to modern diseases. And the original reasons for their extinction may still be threats. Imagine bringing back the woolly mammoth only for it to be poached again for its ivory.
Right, the environment they'd return to is fundamentally different.
And this feeds into the biggest financial hurdle, the cost and conservation trade-off. We're talking about hundreds of millions of dollars being invested into colossal biosciences and other projects just to bring back a handful of species.
Realistically, that funding competes directly with immediate crisis-level conservation budgets.
So if millions are diverted from programs to save, say, the vaquita, with maybe 8 of them left, we could inadvertently weaken those efforts and accelerate the extinction of species still alive today.
It raises a huge question of prioritization. Should the immediate rescue of species on the very edge take absolute priority over resurrecting the long gone?
And then there's the proxy problem again. If the resurrected animal is only a hybrid, it may not even achieve the environmental benefits that were promised. The immense cost will have been spent for an expensive, genetically modified zoo animal.
The final, and I think the most difficult pitfall, is what the sources call the high cognitive ethical dilemma.
This is where the debate moves entirely out of the animal kingdom.
Yeah. The sources highlight the potential application to species like Neanderthals or other hominids.
And the idea of creating sentient beings without a culture, a family structure, or a safe place in our world
It's truly chilling.
It creates a tremendous burden of responsibility. They would likely have self-awareness and capacities for suffering. If we treat them as experimental assets rather than individuals, that presents a profound, maybe unanswerable ethical challenge.
We just have no legal or moral framework for that.
None. And this is why the global conservation community has recognized the gravity of this. The IUCN's De-Extinction Task Force, formed back in 2014, was a massive early step to try and draft some guiding principles before the science got too far ahead of us.
Okay, let's move from the theoretical challenges to the reality of the lab and the field in Section 3. In the lab and the wild candidates and successes, this is where we see exactly which pathways are being applied to which animals.
And we start with the genome editing focus, the Pleistocene giants and iconic birds.
Of course. The woolly mammoth, as we said, it's the flagship project.
It's the ultimate test case for genome editing and proxy creation, since there are no viable cells for cloning.
So George Church's team in Colossal Biosciences are migrating specific genes into the Asian elephant. What are those precise target traits they're going after?
They're focusing on what you could call the cold climate trifecta. Genes for cold-resistant hemoglobin, for oxygen delivery in freezing temperatures.
Okay.
Genes for dense, long, shaggy hair. And genes controlling the accumulation of thick layers of subcutaneous fat for insulation.
And we just saw a fascinating incremental success on this path.
That's right. In March of 2025, Colossal announced the birth of woolly mice. Now, they were careful to note they mostly used known mouse genetic variants, not pure mammoth DNA.
But it's a proof of concept.
It confirmed the capability to successfully edit and transfer complex traits related to temperature regulation and hair structure. It's a necessary de-risking step before trying the much more complex elephant-mammoth hybrid.
Another major target using a very similar method is the thylacine, the Tasmanian tiger, which died out in 1936.
The thylacine is a fascinating, unique challenge because of marsupial biology. Colossal is partnering with the University of Melbourne. They claim a 99.9% complete genome reconstruction as of October 2024.
And they're targeting its closest living relative, the fat-tailed dunart.
Yes, a small, mouse-sized marsupial.
So what's the specific marsupial challenge here?
Well, marsupial gestation is radically different. The baby is born extremely underdeveloped and finishes its development in a pouch. So the hurdle isn't just creating the hybrid embryo, it's engineering the Dunart to successfully carry, birth, and pouch a much larger thylacine Dunart hybrid.
And they're aiming for a revival attempt as early as 2027.
It's ambitious.
Colossal has also tackled the direwolf, which really showcases how this genome editing creates a sophisticated proxy.
Right, the direwolf project, they analyzed fragmented genomes and determined that the direwolf was much more distinct from the gray wolf than we thought.
So they made targeted edits to the genome of the modern gray wolves to replicate the direwolf's distinctive features.
Exactly, which resulted in the three famous pups showcased in April 2025, Romulus, Remus, and Khaleesi.
And this was a proof of concept.
It was designed to show that only minor genetic modifications were sufficient to revive the species' functional characteristics, even without splicing in ancient DNA. It shows how the line between a genetically edited modern species and a proxy is getting very blurry.
We also see iconic birds being targeted, which is especially important for fragile island ecosystems.
The dodo, driven to extinction by humans, is a prime target for Colossal. The goal is restoring biodiversity to Mauritius. Its closest living relative, the Nicobar pigeon, provides the genetic framework.
And the elusive ivory-billed woodpecker.
This bird is considered functionally extinct. There have been no confirmed sightings for decades. Colossal plans to use genome editing on relatives like the pileated woodpecker.
Okay, let's pivot away from the high-tech lab and look at backbreeding in action.
The aurochs restoration is the definitive example here. The Toros program in the Netherlands is actively selecting and crossbreeding primitive cattle breeds
to get an animal that not only looks like the aurochs, but can function as a self-sufficient grazer.
And the objective isn't just historical curiosity, it's ecological. They want to restore its role as a massive keystone species in Europe, maintaining biodiversity by trampling scrub and dispersing seeds.
I saw they're aiming for wild releases in places like the Scottish Highlands by 2026.
It's happening fast. And another great example is the quagga project in South Africa. The quagga was a subspecies of plains zebra, striped only on its face and upper torso.
So they use selective breeding of plains zebras to specifically select for that partially striped look.
Correct. And their goal is immediately functional. They plan to reintroduce these animals to the Western Cape to help eradicate invasive tree species. The quagga proxy is being engineered as a biological tool for habitat management.
Finally, let's look at two triumphs in de-extinction, which often involve plants or species that were only functionally extinct.
We revisit the northern white rhinoceros. The biorescue team in Colossal are actively fighting functional extinction. They are generating embryos using cryopreserved sperm and female egg cells. The goal is to implant these into surrogate southern white rhinos before the end of 2024.
It's conservation using the ultimate genetic tools. And then there's the Yangtze giant soft-shell turtle.
A sad, poignant reminder of how quickly functional extinction can become complete extinction.
The last known female died in 2019.
And another one found in 2020 died in 2023. They are still searching for a female to breed with the remaining males, but it just underscores the razor's edge of urgency.
Now let's talk about a biological miracle, the Judean date palm. This is botanical de-extinction at its simplest and most profound.
The Judean date palm was considered extinct around the 15th century. But in 2005, scientists achieved the oldest successful de-extinction by germinating 2,000-year-old preserved seeds.
2,000 years old? How did they even revive them?
It was shockingly low-tech. Simple hydration and soaking, using a household baby bottle warmer to maintain temperature, along with some fertilizer and growth hormones.
Amazing.
The first male plant to grow was named Methuselah. And then in 2021, a female plant named Hannah produced the first dates grown from this ancient lineage in millennia.
That story is such a powerful counterpoint to the complexity of the mammoth. Sometimes the solution is just simple preservation.
It confirms that seed banking is a robust and essential pathway. We saw similar successes with the York groundsel, extinct in the wild by 2000. Seeds from the Millennium Seed Bank were germinated and successfully reintroduced in York in 2023.
And finally, the Floriana giant tortoise, which is a slow, iterative hybrid recovery.
Extinct around 1850, but scientists found living hybrids on another island, so a breeding program is now back-breeding those hybrids generation after generation to recover the Floriana genetic traits.
And they've had success.
As of 2025, over 400 tortoises have been hatched. It's a multi-generational hybrid-based success story.
We've covered a staggering amount of ground here. From dire wolf pups to ancient palms producing fruit again, it really confirms that the science is accelerating beyond prediction.
The capability is no longer the main issue. the resource allocation, and the ecological consequences are.
As we wrap up this deep dive, let's take a breath and recap the immense tension we've explored between the promise of restoration and the pitfalls of reintroduction.
We've established that de-extinction offers extraordinary technological tools, tools that could potentially save species on the brink, boost genetic diversity, and lead to massive advancements.
But the investment is huge, often diverting scarce resources from immediate crisis conservation efforts. The risks of ecological disruption are very real.
The global conservation community acknowledges this high-stakes game. The establishment of the IUCN's De-Extinction Task Force back in 2014 was a clear and necessary signal that this technology is being taken seriously.
They're trying to draft guiding principles for its ethical use, recognizing we need a moral compass before we fully embrace this power. So what does this all mean for you, the learner, as you process this monumental shift in our ability to manipulate life and death?
Well, given the simultaneous breakthroughs for functionally extinct species like the rhino and for long-dead species like the mammoth, the question of resource allocation is paramount.
That raises an important question. How should researchers and conservationists balance the immense cost and effort?
Should the immediate rescue of species on the very edge, the ones we know can survive today with aggressive intervention, take absolute priority over resurrecting the long gone? Or do the radical advancements gained from pursuing the most difficult projects, like the mammoth, offer the only long-term hope for saving all life by fundamentally changing the tools we have available? That tension between immediate rescue and future-proofing all life is the defining moral and fiscal challenge of the resurrection biology era.
Welcome to The Deep Dive, the place where we take complex, essential information and distill it down to the core truths you need to know.
Today, we are strapping in for a deep dive that looks past the software glamour of artificial intelligence.
Yeah, we're focusing squarely on the concrete, the physical infrastructure that is actually powering this entire AI revolution.
It's so easy to think of AI as, something purely digital, just a brilliant algorithm that sort of runs on thin air.
Right.
But the reality, and our sources made this incredibly clear, is that this monumental technological leap we've seen, largely triggered by ChatGPT back in late 2022, it's actually a colossal, unprecedented demand on global resources.
We're not talking about just gradual growth, are we? This is a physical infrastructure phenomenon. It's new continents of electricity, mountains of specialized hardware, and billions of gallons of water.
Exactly.
So our mission today is to really unpack the specialized world of the AI data center. This is a facility that is just fundamentally different from any server farm that's been built before it.
And we need to understand its unique and, frankly, terrifying architecture.
Yes, and the staggering financial engineering that's fueling its construction, and also the palpable immediate costs that are being imposed on electrical grids and, local communities all over the world.
And if you need just one sort of initial data point to get your head around the shift we're talking about, just look at power density.
Okay.
A standard traditional data center, the kind designed for web hosting or, basic company functions, typically draws about 5 to 10 kilowatts of power for every server rack.
5 to 10, that's the baseline.
Yeah.
So how does that compare to these specialized AI facilities?
Well, our sources show that an AI data center is consuming upwards of 60 kilowatts per rack. 60. And often much, much more. We're talking about 6 to 10 times the energy consumption in the same physical space.
Wow.
And that tenfold increase in density and power demand, that is the entire reason the financial risks and environmental implications we're about to explore are escalating so severely and so quickly.
Okay, so let's unpack that enormous energy spike. We have to start with the specialized architecture, right? Because every single one of those extra kilowatts is generated by the hardware inside.
Exactly. The engine of this new revolution is not the CPU, the central processing unit, which has governed computing for decades.
Right.
It's the specialized computer chip, primarily the GPU or graphics processing unit, and similar chips like Google's TPUs, their tensor processing units.
And these chips are designed for one thing, really. It's about performing thousands of parallel calculations all at the same time, which is exactly what machine learning needs.
And what's fascinating is just the power profile of these chips. I mean, they're workhorses, but they are incredibly power hungry.
How hungry are we talking?
A single top-tier GPU can use 2 to 4 times as much energy as a standard CPU. It's often pulling between 250 and 500 watts.
And the key word there is single. If you're building a standard server farm, you're maybe optimizing for efficiency, for space, but with an AI training facility, you are all about speed.
All about speed.
Which means you need those chips to be able to communicate with each other instantly. And that's where this density problem really begins.
Precision is just critical here. To train a large language model quickly, the massive amounts of data being processed have to migrate rapidly between thousands of these specialized chips. You just can't afford any latency.
So you can't spread them out.
You can't. So instead of spreading them out, developers pack thousands of these 500-watt chips tightly together in these high-density server racks, all connected by specialized high-speed cables.
And that density, all that high-wattage silicon packed into a tiny area, that's what jumps the power consumption from what, 5 kilowatts up to 60-plus kilowatts per rack?
That's the leap.
So if the density creates this terrifying heat problem because every watt of electricity consumed eventually turns into heat, why is there such resistance to just separating the chips? Why do they have to accept this colossal cooling headache?
It just comes down to performance. It's a race for technological supremacy. If you slow down the data migration between the chips, you slow down the training of the model.
And if you slow down the training, you lose the race.
You lose the race. The industry has decided that the cooling and power headache is worth the speed increase. But that heat, it can't be managed with standard airflow and air conditioning. It's just too much.
And that's why we're now seeing the development of these entirely new, far more resource-intensive cooling techniques.
Which, immediately introduces the massive energy and water consumption issues we'll get into a little later.
Let's look at a couple of specific examples of these new cooling techniques right from our source material. Take Google, for instance.
Okay.
They've been at the forefront of this, developing systems that pump large amounts of water through pipes that run right next to the chips. It's basically a heat exchange unit.
And this method is incredibly effective at carrying that extreme heat away, but it puts immediate localized strain on nearby water supplies. It requires huge volumes of water.
And that water often ends up evaporating or it gets discharged warm, which is why local communities start protesting pretty quickly.
Right. And then you have the alternative, which tries to conserve water, but, well, it demands a massive amount of electricity instead.
You're talking about companies like Scale.
Exactly. Scale, another data center operator, they circulate water for cooling, but then they use these massive, large electric chillers to cool that water back down so they can reuse it.
So there's an immediate trade-off there.
The huge one. You can conserve water by recycling it, which is good, but operating those enormous chillers significantly increases the total electricity draw of the entire facility.
So you're just shifting the environmental burden from water depletion over to grid strain.
It demonstrates that there's no easy fix to the density problem. Every single solution leads back to this colossal demand for either electricity or water, or both.
So let's just connect the dots before we move on. The foundational need is for specialized, power-hungry silicon.
GPUs.
That leads directly to hyperdense server racks for speed. Hyperdensity creates extreme heat,
which leads to specialized cooling solutions that burn staggering amounts of water or staggering amounts of electricity.
And all of these architectural necessities, they really set the stage for our next section. The sheer, almost unbelievable amount of money being thrown at this infrastructure challenge.
This is where it gets really interesting. We are no longer talking about standard corporate budgets. We're talking about financial velocity at a scale that is, it's re-engineering global capital flows.
This truly is a gigawatt gold rush.
It is. Just look at the spending pace. Our sources cite that between January and August of 2024 alone, that's just 8 months.
8 months.
The 4 largest hyperscale giants, Microsoft, Meta, Google, and Amazon, collectively poured $125 billion into building out their AI data center capacity.
$125 billion in under a year. That just underscores the panic, the urgency driving this whole build-out.
And that figure is really only the beginning. The future forecasts are staggering, though they do reflect a massive degree of uncertainty around future costs.
What kind of numbers are we seeing?
Well, Citigroup forecasted $2.8 trillion would be spent globally on AI data centers by 2030.
2.8 trillion.
But then McKinsey and Company threw an even larger number out there. They estimated nearly $7 trillion globally by that time.
Let's just pause on that. Why such a huge difference between 2.8 trillion and 7 trillion? That gap itself tells the story, doesn't it?
It tells you how volatile and unknown the future cost structure is. The smaller number might focus only on, say, direct capital expenditure, just building the centers.
Right, the construction costs.
While the larger 7 trillion figure, that likely includes all the upstream costs, the necessary utility grid upgrades, the price inflation for the specialized chips, the operational costs of running these places for a decade.
But whether the true number is 3 trillion or 7 trillion, we're talking about a monumental global redirection of resources. This is rivaling major historical infrastructure projects.
And we're seeing this velocity reflected in the financial markets immediately. S&P Global noted that in 2025, $61 billion was spent just on the data center market. And debt issuance related to the sector reached $182 billion that year.
And naturally, this frenzy has created instant new wealth. We're seeing executives from specialist providers like CoreWeave, Grok, and QTS becoming new billionaires in the process.
To really understand who's driving this, we kind of need to categorize the operators. There are two distinct groups, and they're leveraging different funding strategies.
Okay, so who are they?
First, you have these established players, the hyperscalers. These are the large tech companies you already know.
Google, Meta, Microsoft, Oracle, Amazon.
Exactly. They build at massive scale, often for their own proprietary use or for offering general cloud services.
And then you have the neoclouds. I saw the New York Times describe them as a new generation of data center providers.
That's a good way to put it. Companies like CoreWeave, Nebius, and Lambda, they're specializing specifically in hosting these massive, power-intensive GPU clusters for machine learning. CoreWeave is frequently cited as the most prominent U.S. operator in this space.
And here's a fascinating crossover. Our sources note that several companies that were previously deep in energy-intensive cryptocurrency mining,
like Bitdeer, TeraWulf, CleanSpark.
Right. They're now quickly retooling their existing sites that already have these enormous power connections, to meet the AI demand instead.
It's a natural shift, really, from one high-powered digital industry to another.
This financial acceleration really culminates in these mega projects, which just illustrate the industrial scale we're discussing. Let's start with the one that's generated the most headlines, the Stargate project.
Stargate. Announced in January 2025. It's a massive partnership between OpenAI, Oracle, and SoftBank.
And it's composed of 6 built or proposed AI data centers in the United States.
And the Stargate project, it reveals the profound implications of this build-out on the entire global supply chain, not just the power grid. The consortium secured an upstream agreement with Samsung and SK Hynix.
For what?
To supply the project with 900,000 DRAM wafers per month.
900,000 DRAM wafers a month. To put that in context for you, DRAM is the dynamic random access memory that is essential for, well, for all computing, but especially for AI.
And the fact that one project, Stargate, is designed to consume roughly 40% of all global DRAM output.
40%.
40%. It suggests a critical supply chain crunch is coming. What does that mean for the rest of the tech ecosystem?
It means that if you're trying to build a new laptop or a gaming console or even a smaller enterprise server, you might face delays and extreme price inflation.
Because 40% of the world's immediate supply is being funneled to satisfy the needs of just 6 AI data centers.
It shows that AI isn't just competing for electricity, it's competing for the physical building blocks of the entire global digital economy.
And now let's look at the competition. Amazon launched Project Rainier in Indiana, an $11 billion project, specifically to house models from the company Anthropic.
This project is planned for 30 individual centers, and it's expected to consume a staggering 2.2 gigawatts of electricity.
Just for context, 2.2 gigawatts is the capacity of a large nuclear power plant.
For one project.
And then you have Meta. Their flagship, Hyperion, is expected to use 5 gigawatts. Their Ohio project, Prometheus, is a 1 gigawatt facility.
These demands require equally massive financial engineering to offload the risk from the main corporation.
This is where the financial concepts get fascinating and often pretty opaque.
How is a company like Meta funding a $30 billion project like Hyperion without dramatically increasing its direct corporate debt.
They use what are known as special purpose vehicles, or SPVs.
An SPV, so think of it like a financial firewall.
That's a good way to put it. Instead of Meta taking out a $30 billion mortgage to build the data center, they create a separate, legally distinct company, the SPV, to own the property and take on the debt.
And then the SPV raises the money through bond offerings.
Exactly. And the beauty for Meta is they just rent the space from the SPV. The $30 billion Hyperion transaction, for example, was structured by Morgan Stanley and funded by a bond offering from major players like Blue Owl Capital and PIMCO.
And these bonds were then sold to huge institutional clients like BlackRock.
So this financial structure does two key things. It shields Meta's balance sheet from the direct debt risk of a potential AI bubble, and it draws massive amounts of private credit money held by hedge funds and investment banks into infrastructure development.
So big tech avoids the direct risk, but that risk is just distributed across the broader financial ecosystem, right down to pension funds managed by firms like BlackRock.
Precisely. And this strategy gets even more tangible when you look at the neoclouds. Since they don't have decades of steady revenue like the hyperscalers, they have to get creative with their collateral.
What are they using?
CoreWeave, the most prominent U.S. neocloud, has actually leveraged its most valuable physical assets, the NVIDIA chips themselves, as collateral for huge GPU-backed loans.
Wait, but if we know these GPUs have short lifespans, sometimes just a year, isn't that asset too volatile to be collateral for a billion-dollar loan? What happens when the chip burns out?
That is the critical question, and it illustrates the insane confidence investors have in this AI boom. As of December 2025, CoreWeave took out 3 such loans, collectively worth $12.4 billion.
From who?
From major banks and private credit firms, including Goldman Sachs and Blackstone.
So why are these physical chips better collateral than traditional company bonds?
Because they're tangible, they're in extremely high demand, and they have proven residual value. If CoreWeave defaults, the lenders can just seize the highly sought-after chips and sell them on the open market immediately.
The physical chip itself is the foundation of this $12.4 billion debt structure.
That is truly the definition of a gold rush. We've gone from the intangible value of software to the physical silicon chip being used as collateral for billions in financing.
But as we transition to the next section, we have to recognize that this financial boom is creating a monumental real-world cost.
We established that AI data centers use dramatically more power. And when you multiply that hyperdensity by the dozens of mega projects we just discussed, the demands, they go from being merely large to being fundamentally destabilizing for existing infrastructure.
The scale is almost impossible to comprehend without specific comparisons. The average AI data center has an electricity footprint equivalent to 100,000 typical households.
Right. But the International Energy Agency estimated that the largest centers currently under construction, like Meta's Hyperion or Amazon's Rainier, could consume as much electricity as 2 million households.
2 million?
Think about that. A single campus of buildings consuming the energy equivalent of a major metropolitan area. Meta's Hyperion alone is expected to require 5 gigawatts of power.
And consider that 3,200-acre DC in Pennsylvania, built on an old power station site, which is capable of consuming 4.5 gigawatts. That kind of demand just sends shockwaves through regional power grids.
So where's all this energy coming from? Can the clean energy transition even keep up?
That's the big question.
And unfortunately, the current mix is heavily reliant on fossil fuels. In the U.S., data centers are primarily powered by natural gas. That's about 40% of their consumption.
Then renewables.
Renewables, while growing, are still only at 24%, followed by nuclear at 20% and coal at 15%.
So experts and utility companies are warning that renewables just can't be deployed quickly enough to fulfill the sheer velocity of this demand.
Exactly. The Associated Press reported that the energy for these new AI data centers would likely be sourced from the cheapest, most readily available options.
Which often means dispatchable fossil fuels like natural gas or oil.
And this reliance is leading to some deeply concerning on-site power solutions that bypass the grid altogether, but with significant environmental consequences.
Like what?
Well, take xAI's Colossus project. It's reportedly planning to use on-site gas turbines for power generation.
Or that 3,200-acre site in Pennsylvania we mentioned. It's relying on 7 separate 30-acre gas generating stations supplied by the natural gas giant EQT.
This isn't just plugging into a wall. It's building miniature fossil fuel power plants right next to the data centers.
And we see this trend dramatically with companies like VoltaGrid. They're proposing to install 33 reciprocating internal combustion engines, or RICE engines, at a site in Georgia.
RICE engines.
Hmm.
To give you a picture, they're basically massive industrial-grade internal combustion generators. Think of huge, powerful truck or marine engines.
And they're typically used for emergency backup power.
Right. The fact that a data center needs 33 of these for its baseline power suggests they just cannot trust the existing grid for a reliable, continuous supply.
And what are the environmental consequences of deploying so many of them?
The emissions are significant, and they're local. RICE engines are known to emit harmful pollutants, PM 2.5, nitrogen oxides, volatile organic compounds. These directly impact air quality in the immediate vicinity.
Which is often a semi-rural or even a residential area.
And what does this all mean for the consumer? I mean, we talk about grid strain, but what does that mean for an average household?
Are we talking brownouts or just higher utility bills?
It's primarily higher utility bills. It's driven by infrastructure costs. Utility companies are forced to make massive, rapid, and costly upgrades to handle these sudden gigawatt demands.
And those costs are typically socialized, meaning they're passed on to all consumers, whether they use the AI data center or not?
This strain has led to severe warnings from grid operators. The independent monitor for the PJM interconnection, which manages a huge power grid across 13 states, explicitly warned that the pace of new data centers simply cannot be supported by the current infrastructure.
And they advocated for a federal moratorium on construction.
In response, policy is shifting rapidly to favor the builders. The Federal Energy Regulatory Commission, FERC, published an order allowing data centers to connect directly to power plants.
Bypassing the public grid, that seems like a massive regulatory shortcut. What are the implications of that?
Well, the intention is speed. It gets the power to the facility faster. But it can create instability in the broader system, and it reduces public oversight.
And more concerning still is the political rhetoric now supporting the most carbon-intensive solutions.
Yeah, the U.S. Secretary of Energy expressed support for unretiring older coal plants, specifically to power new AI data centers.
The unretirement of coal plants, that has a really stark and severe social justice connection that we have to explore.
Absolutely. When we talk about that connection, we're referring to the fact that these older coal plants, often called peaker plants, have historically been located disproportionately near marginalized communities and communities of color.
And now they're being kept open or restarted solely for big tech's AI projects.
Which means those specific, often low-income communities continue to bear the health burden of sulfur dioxide and particulate emissions so that trillion-dollar companies can train their models.
That is a profound cost of progress. Okay, moving beyond electricity, we face the second major resource crunch, the water problem.
This is driven by those specialized cooling demands we discussed earlier. The numbers are alarming here, too.
What are we looking at?
The Department of Energy reported that U.S. data centers used about 17 billion gallons of water per year in 2024.
Okay.
But due to the rapid proliferation of AI servers, that usage is forecasted to skyrocket to nearly 80 billion gallons per year by 2028.
That's a massive fourfold increase in just 4 years.
And the impact is already being felt on the ground. We mentioned Amazon's Project Rainier in Indiana. During construction, the site pumped millions of gallons of water out of the ground in a process called dewatering.
And as of mid-2025, state officials launched an investigation into whether this process directly caused dry wells for local residents living nearby.
The corporation gains a resource, the local residents lose their basic water supply.
And at the same time, we're seeing data centers move into regions like the Great Lakes area, where water levels are already falling.
And the arrival of these massive new facilities, which are now being explicitly designed to use water for cooling, is raising huge environmental alarm bells across multiple states.
We also shouldn't overlook the other footprints here. The immense stress of machine learning means GPUs have a short lifespan, 1 to 8 years, creating a major e-waste problem.
Plus the sheer physical scale. The 3,200-acre sites, the 30-building campuses, that requires massive amounts of cement and concrete, both of which are huge emitters of greenhouse gases.
The physical environmental cost of this digital revolution is just compounding across electricity, water, air quality, and waste.
Given the colossal scale and the severe environmental impact we've just detailed, you'd expect a strong, unified response against this build-out.
But what we actually see is this strange paradox. Fierce bipartisan support at the federal level, colliding with intense bipartisan resistance on the ground.
The federal support is undeniable. Both the Biden administration through an executive order in January 2025 and the second Trump administration with its AI action plan have actively supported rapid data center construction.
And it's generally framed around the imperative of American technological supremacy in the AI race.
And this federal support is heavily guided by a powerful lobbying force, the AI Infrastructure Coalition, or AIIC.
This coalition is led by high-profile figures like Senator Kyrsten Sinema, and it includes pretty much every major stakeholder in this gold rush.
You've got big tech Google, Meta, you've got data center providers QTS, Digital Realty, and crucially, you have the energy giants.
Utility companies like Duke Energy and fossil fuel companies like ExxonMobil and Nextera Energy.
When you have the oil giants, the major utilities, and big tech all aligned, their political leverage is immense.
But the backlash is widespread and it's decentralized. Local communities in over a dozen states, Michigan, Texas, Virginia, Arizona, have successfully resisted, delayed, or just outright rejected projects.
And critically, this local opposition is not tied to one political party. It's a community-level reaction to immediate, tangible threats.
What are the consistent concerns driving that resistance?
They're highly localized. Residents complain about intense noise pollution, the constant hum of massive cooling fans. They cite air and water pollution risks. They worry about traffic during construction.
And, perhaps most importantly, they observe that the investment doesn't really translate into local prosperity. This is the job creation bust critique.
Exactly. Critics argue these billion-dollar facilities create hundreds of temporary construction jobs, but once they're operational, they only require a small handful of highly specialized technicians.
So residents are left with the environmental consequences, property devaluation, and almost no lasting economic benefit.
And this broad opposition has led to a major push for intervention. Over 230 diverse groups, from the NAACP to Greenpeace, and figures like Senator Bernie Sanders have formally supported a federal moratorium on new data center construction.
Compounding all this conflict is the issue of corporate secrecy.
Right. Large tech companies often use shell companies and require public officials and landowners to sign non-disclosure agreements,
Which effectively hides the true scope of the project until it's too late for local resistance to mobilize.
We saw the consequences of this vividly in Michigan with a joint OpenAI Oracle data center that's part of the Stargate project.
What happened there?
When a local township initially rejected the massive proposal, the developers simply sued. Following a settlement where they got the land, they still needed rapid power approval.
And how did they manage to get that while bypassing public input?
They used an ex parte motion before the Michigan Public Service Commission.
An ex parte motion, to explain that simply, it's a request made by one party, in this case the developers, to a judge or commission without having to notify or involve the opposing parties, which was the public.
And this move allowed the commission to approve power provision to the data center without any public hearings or input. It shows how entrenched developers can use the regulatory system to bypass local outrage.
The pace of this gold rush also introduces significant economic vulnerability, which is feeding fears of an AI bubble.
Indeed. The construction is moving at a reckless speed that risks rapid obsolescence. We already know the GPUs have an extremely short lifespan because of the stress of machine learning training.
So if the next generation of specialized chips arrives, and they inevitably will, the existing data centers could require massive, immediate retooling.
Which leads to this concept of stranded assets. If a tech shifts or if the economic demand for AI modeling softens, there are major concerns that these multi-billion-dollar data centers could just become obsolete.
And there was a warning in Wisconsin that highlighted that if a data center fails, energy customers could be left paying for the unused infrastructure upgrades that utilities were forced to build.
Furthermore, one hedge fund founder poured some cold water on the whole sector, concluding that these AI data centers, built at such phenomenal expense, would need to generate about $1 trillion of cumulative revenue just to achieve long-term profitability.
The scale of the investment versus the highly stressed, short lifespan hardware, it introduces undeniable financial risks to the broader global economy.
And just when you think the problems are confined to the terrestrial grid, the final pivot shows the ambition has become literally astronomical.
You're talking about building data centers in outer space.
It sounds like science fiction, but it's a direct response to the terrestrial constraints we've been discussing. Google announced Project Suncatcher, with plans to test its TPU chips in space by 2027.
And NVIDIA-backed StarCloud has already launched a satellite with an H100 GPU and used it to train the first large language model, NanoGPT, in space.
What's the logic there? Is it just a cool novelty?
The primary driving force is escaping resource constraints. In space, they can potentially harness massive amounts of continuous off-grid solar power and use the vacuum for passive high-efficiency cooling.
bypassing the twin headaches of grid strain and water depletion entirely.
The fact that companies are willing to invest in launching infrastructure into orbit underscores exactly how severe and unresolvable the terrestrial crisis has become for them. It's the ultimate attempt to escape the confines of the power grid, water regulations, and local opposition.
So what does this all mean for you watching this infrastructure war unfold? We've seen the high-stakes paradox of the AI era. The technological ambition is boundless, exemplified by companies using their chips as $12.4 billion in loan collateral.
Or planning orbital data centers to escape environmental limits.
But this immense, dizzying ambition is fundamentally grounded by immediate and severe physical costs. We have power grids straining, the unretirement of controversial coal plants, and local communities suing over water depletion.
And regulatory circumvention through things like ex parte motions.
The sheer velocity of development, dramatically illustrated by that Stargate project requiring 40% of global DRAM output, suggests a critical takeaway.
Which is?
That hardware and resource constraints, not software innovation, may become the ultimate limiting factor for artificial general intelligence. If the world's most advanced models can't be trained without drawing down critical global supplies and stressing outdated grids, then the rate of AI progress is tied directly to physical capacity.
When the world's most cutting-edge learning models are being trained using energy sourced from reactivated, socially controversial coal plants, it forces us to ask a profound question. What does that fundamental tension tell us about the true, non-digital cost of progress, and who, precisely, is responsible for paying it? It's a calculation that we, the global community, are only just beginning to reckon with.
Okay, let's unpack this. We're diving into one of the most intriguing lost lands ever conceived, Lemuria, or sometimes you'll see it referred to as Lemuria. Now, if you think you know the story of sunk continents from legends like Atlantis, well, this one offers a far more bizarre and fascinating journey.
It really does.
Because unlike Atlantis, which began as a philosophical fable from Plato, Lemuria started in the sober, exacting world of 19th century zoology.
And that's the critical difference, isn't it? It frames this entire deep dive. Lemuria wasn't, invented as a myth. It was initially a required geographical solution to a profound biological mystery.
Right. So our mission here is to trace that incredible and, frankly, unexpected arc.
We're looking at a hypothetical lost continent originally proposed back in 1864, which was theorized to have just sunk beneath the Indian Ocean.
And its intellectual lifespan is absolutely wild. It went from a strictly scientific fix for a biogeographical riddle, gained this immense cultural traction as the supposed cradle of humanity, and then, and this is the crucial part, transformed into a foundational cornerstone of mystical doctrine.
Especially theosophy.
Exactly. And it's thrived in the popular imagination long, long after science had decisively rejected it.
Our sources, when you look at them all together, they reveal this classic case study. It shows precisely how an intellectual necessity, a theory you need to make sense of the natural world in a specific era, can be completely decoupled from its scientific evidence and then reappropriated and sustained by cultural imagination and, well, spiritual needs.
So the mission for you, our listener, is straightforward. We're going to follow this idea as it jumps fields. We'll explore the specific biological puzzle that forced Philip Sclater to invent Lemuria.
Then the massive geological discovery that later discredited it, the whole story of plate tectonics.
Yes. And finally, its enduring, bizarre, and multifaceted life in the popular imagination, which spans from Theosophy's human evolution timeline to, get this, a literal subterranean civilization supposedly living under Mount Shasta in California.
To really appreciate why anyone would invent a new continent and, give it a name like Lemuria, we have to immerse ourselves in the scientific context of 1864.
Right.
And this is where we meet the zoologist and biogeographer Philip Sclater. He was wrestling with what we now call a classic problem of animal distribution, focused entirely on primates in the Indian Ocean region.
The famous lemur problem. Okay, so for those of us who haven't spent a lot of time thinking about primate geography, what exactly was Sclater seeing in the fossil record that demanded such a radical solution as a lost continent?
Well, he was puzzled by the profoundly discontinuous distribution of animals that he classified as lemurs. And it's important to note, Sclater's classification of lemurs at the time was quite broad.
So not just the lemurs we know today from Madagascar.
No, it also included related primitive primate groups that were found elsewhere.
And the mystery wasn't just where they were, but how on earth they got there.
Exactly. He had undeniable evidence fossil remains of these creatures on the island of Madagascar, which, of course, is globally famous for its living lemur populations today.
Sure.
But he also found corresponding ancient fossils of closely related species on the Indian subcontinent, thousands of miles away.
Wow.
Now, here's the crucial observation. They were conspicuously, frustratingly absent in continental Africa.
Which is geographically quite close to Madagascar.
Very close. And also absent across the entire Middle East.
That's a massive gap. I mean, if evolution and species diffusion follow a gradual path, moving across continuous land masses, how did they leapfrog an entire continent and an ocean to settle in those two widely separated regions?
They couldn't.
You can't exactly swim that distance.
No. And it creates a severe, almost unbelievable discontinuity in biogeography. How did this ancient lineage get from point A, which is Madagascar, to point B, India, without leaving a single trail or trace in any of the massive land masses lying in between?
And we have to remember the intellectual limitations of the mid-19th century. We didn't have plate tectonics.
Not at all.
The prevailing geological worldview was that continents were essentially fixed. They didn't drift horizontally.
Right.
So if a species couldn't swim and couldn't fly, and the continents couldn't move, then the only logical solution was, well, there must have been a physical land connection.
A land connection that allowed them to walk across.
And that connection must have since vanished, sunk.
That's the elegant, if ultimately incorrect, hypothesis of the sunken land bridge, which Sclater proposed. He put forth the idea that, and I'm paraphrasing here, a large continent occupied parts of the Atlantic and Indian Oceans, which subsequently broke up.
And his conclusion was that places like Madagascar and the Mascarene Islands were just leftover.
Exactly,
Yeah.
just the existing high-standing relics of this great lost landmass.
And he didn't just propose the concept, he gave it that now immortal name.
He did. He proposed the specific name, Lemuria, derived directly from the family of animals, the lemurs, whose inexplicable distribution necessitated its very existence.
That really speaks to the perceived scientific necessity of the concept at the time. It wasn't fantasy. It was a required mechanism to explain observable data within the reigning geological paradigm.
It's a powerful moment in scientific history because it shows the desperation to categorize and explain life after Darwin.
Well, that makes sense.
The acceptance of Darwinism spurred this intense global need to trace the diffusion of species from their points of evolutionary origin. You suddenly needed a route map.
So scientists were under immense pressure to figure out how species got from their evolutionary birthplace to where they were currently observed.
Right. And because they believed the continents were fixed, biologists and geologists alike frequently postulated these submerged land masses to account for species or even rock formation resemblances separated by water barriers.
So Sclater was working within a pretty well-established intellectual framework.
Absolutely. In fact, our sources remind us that he wasn't even the first to suggest a southern landmass to solve this specific problem. Yeah, about 2 decades before Sclater published, a French naturalist named Étienne Geoffroy Saint-Hilaire had already suggested the existence of a massive southern continent to explain similar animal relationships between India and Madagascar.
So why do we remember Sclater?
Well, Saint-Hilaire hadn't given the landmass a memorable specific name like Lemuria. And that name, that branding, is why Sclater's concept gained so much traction.
And the land bridge idea was so central to the thinking of the era that it became a systematic study.
Oh, completely. The need for these bridges was so acute that years later, the geologist Melchior Neumayer dedicated a systematic effort to cataloging all these hypothetical structures in his comprehensive 1887 work, Erdgeschichte.
Which is German for history of the earth.
Right. And Lemuria, alongside numerous other proposed land bridges spanning all the oceans, found a legitimate, if temporary, home in that era of intense geological and biological speculation.
So we established Lemuria as a true scientific tool. A logical deduction based on the best available data, solving the dispersal puzzle of ancient primate groups across the immense barrier of the Indian Ocean, grounded in the prevailing belief that land masses sank vertically. Okay, here's where the story takes its first radical turn. and where it gets really interesting.
Mm.
Lemuria had solved the lemur problem, but it might have just, faded away as scientific fashion shifted. Instead, the hypothesis exploded in popularity.
It did.
When it moved beyond the realm of zoogeography and into the ultimate question, human origins.
That intellectual jump is primarily thanks to the renowned Darwinian taxonomist Ernst Haeckel.
Haeckel was a towering figure in biology in the 1870s, but he had a huge professional frustration finding the missing link.
Precisely. Haeckel was a fervent advocate of Darwinism, and he desperately needed to establish a clear evolutionary bridge between non-human primates and early humans.
He even came up with a name for it, didn't he?
He did. He coined a hypothetical species name, Pithecanthropus alalis, which means the speechless ape-man. The problem was that the human fossil record was frustratingly, infuriatingly incomplete. He needed a geographical origin point where that critical evolution occurred.
And he sees Sclater's proposed continent and realizes it offers the perfect solution, not just for lemurs, but for us.
In 1870, Haeckel appropriated Lemuria, proposing it as the ancestral cradle of human life. The key brilliance of this move was that it solved two problems at once.
It named an origin point.
And it offered a perfect explanation for the continued absence of fossil evidence.
Because if the continent sank, the fossils went with it.
Exactly. He argued that the fossil record was absent from continents like Africa, Europe, and Asia because the evolutionary steps occurred in a location whose evidence was subsequently destroyed, rendered inaccessible when the entire landmass disappeared.
That connection to the ultimate question, where did we come from, catapulted Lemuria out of specialized journals and ensured its massive popularity across intellectual and public spheres.
It went from solving a niche zoological distribution problem to providing the definitive answer for human ancestry.
But even as its cultural fame skyrocketed, the very foundation of Lemuria was beginning to crumble, thanks to a completely different set of scientists looking at completely different data.
That's the tragic irony for the Lemuria hypothesis. Its scientific life was relatively brief. The concept was rendered completely obsolete, a process we call supersession, with the growing acceptance of Alfred Wegener's theory of continental drift.
Wegener presented his ideas as early as 1912, but it took decades for the scientific community to fully embrace them, right?
That's right. The shift wasn't instantaneous. Wegener's theory was highly controversial at first. It lacked a clear mechanism for why the continents moved.
So it wasn't until much later.
Not until the 1950s and 60s, with the gathering of deep-sea evidence and the refinement of the broader theory of plate tectonics, that the concept achieved widespread acceptance. But once it did, it explained everything the land bridge hypothesis tried to solve, without needing any bridges to sink.
So, plate tectonics is the ultimate killer of Lemuria. How exactly does it solve Sclater's original lemur problem in a way that is scientifically superior?
Well, it shifts the entire geological paradigm. It moves from vertical movement, the sinking Sclater relied on, to horizontal movement, or drifting.
Right.
The modern understanding solves the problem elegantly. Madagascar and the Indian subcontinent were indeed once part of the same massive landmass.
The supercontinent, Gondwana.
The ancient supercontinent called Gondwana, they weren't linked by a bridge, they were physically joined.
Okay, that makes sense.
Specifically, the landmass included the microcontinent Mauritius. They were one piece of continental crust that subsequently began to rift and drift apart millions of years ago.
So India broke away first.
India broke away first, undertaking this rapid journey north to eventually collide with Asia. Madagascar split off later. The distribution of those ancient lemur populations, which Sclater found in the fossil record, is simply explained by the fact that they were living on the same continuous piece of land before it fractured.
So the lemur populations in India and Madagascar are separated because the crust moved apart, not because the land sank into the ocean floor.
That is the crucial distinction. Sclater relied on the idea of isostasy, that a land bridge could simply depress and disappear beneath sea level. Plate tectonics showed that the vast majority of the landmass broke apart due to rifting and plate movement.
And the idea that an entire massive continent just catastrophically subsided beneath the sea became geologically untenable.
Completely. Once plate tectonics provided a vastly more comprehensive and evidence-backed explanation, the intellectual need for the hypothetical Lemuria dissolved.
Wait, if the land didn't sink, was Sclater's entire scientific method flawed? Or did he just lack the necessary geological tools?
Oh, he absolutely lacked the tools. His method, using biological discontinuity to infer geographical features, was sound for the time. He just worked under the false premise of fixed continents.
So he was almost right.
In a way. It's a testament to the power of new information. His conclusion was almost right, the lands were connected, but his mechanism for their separation was fundamentally wrong.
Although, let's pause and acknowledge that sunken land masses do exist in reality, which often confuses this conversation.
That is vital to acknowledge. Our sources make it clear that sunken continent-sized pieces of crust are a geological reality.
But they don't fit the needs of Sclater's Lemuria.
No. Examples include Zealandia, which is 94% submerged beneath the Pacific, or the Kerguelen Plateau in the Indian Ocean. And in Slater's area of interest, we now know about Mauritius, a microcontinent whose fragments are buried under places like the island of Mauritius today.
So geologically, we know pieces of continent can subside or break away, but none of these real examples fit the profile of the massive, catastrophic land bridge that would have facilitated the specific animal migration Sclater described.
Exactly. Sclater was technically correct that Madagascar and India were once connected via a shared landmass, but his mechanism sinking vertically was incorrect. And the location and timeline. It simply doesn't match the modern, drift-based understanding of Gondwana's breakup.
And once science adopted drifting, it left a massive, compelling origin story just floating loose.
And that's when the occult world happily picked it up. The scientific community fully embraced plate tectonics by the 1960s, removing Lemuria from academic discourse. But the idea, thanks to Haeckel's popularizing it as a human origin story, had already been seized and immortalized by the world of mysticism decades earlier.
Let's turn the page now in the intellectual history and look at the cultural vacuum that science left behind. A vacuum for a sublime, hidden ancestry, which was filled entirely by one person. Helena Blavatsky.
Blavatsky, the principal founder of Theosophy, is the crucial figure here. In the late 19th century, she immediately integrated Lemuria into her massive, syncretic, mystical religious doctrine.
She didn't just borrow it, she made it central.
Absolutely. She took Haeckel's connection to human ancestry and transformed it, placing Lemuria into a detailed, specific, esoteric chronology.
She claimed Lemuria was the home of the human ancestors, whom she explicitly referred to as the Lemurians, incorporating them into her complex system of spiritual evolution known as the root races.
We should probably pause and clarify that term for our listeners. What exactly were these root races in Blavatsky's system?
Right.
Well, the concept of root races is central to Theosophy, detailed heavily in her work, The Secret Doctrine. It posits that humanity evolves in a sequence of 7 distinct, spiritually and physically different races over vast geological epochs.
And Lemuria was the third one.
Lemuria, in this scheme, was the home of the third root race. The first 2 were ethereal and spiritual, existing before physical bodies were fully formed.
So the Lemurians were the first truly physical humanity, but still highly spiritualized.
Precisely. They were the key evolutionary step. Blavatsky described them as androgynous, enormous, ape-like beings who developed physical bodies and eventually reproduced sexually.
And their downfall.
The sinking of Lemuria came after they had fallen into physical matter and started abusing their magical powers. This sequence creation, evolution, spiritual fall, cataclysmic destruction is key to all lost continent myths.
This was incredibly influential. Blavatsky's writings had a massive impact on Western esotericism, giving the Lemuria myth a longevity far beyond any scientific reality.
Absolutely. Theosophy ensured Lemuria survived. And what's fascinating here is that the occult concept of Lemuria is fundamentally tied to the belief that it was the location of the emergence of complex foundational knowledge systems.
The original source of wisdom.
The spiritual truths that later religions and beliefs were supposedly based upon. It becomes the ultimate hidden source of all ancient wisdom, preserved only by a select few.
So Lemuria is no longer just a stepping stone for lemurs, or even just early humans. It's a vessel for profound spiritual knowledge. But the myth evolved even further. It moved geographically.
It did. It started in the Indian Ocean, but for many occultists, it moved across the globe to the Pacific.
The Great Pacific Shift.
Exactly. Driven largely by later fringe authors, most notably James Churchward in the 20th century. He took Blavatsky's basic premise of a submerged ancient continent, but developed the concept in immense pseudo-archaeological detail, relocating the lost continent firmly to the Pacific Ocean and giving it a new name, Mu.
And he popularized Mu through a staggering array of books that became hugely successful in the 1920s and 30s.
Oh, yes. His work started with The Lost Continent of Mu, the Motherland of Men in 1926. He followed that with The Children of Mu, the sacred symbols of Mu, and several others.
And he claimed he had proof.
Churchward claimed he had discovered evidence of Mu from sacred tablets in India, which he supposedly translated. The relocation to the Pacific allowed him to connect Mu to South American and Polynesian cultures, vastly expanding its cultural scope.
That borrowing is wild. So Mu was already floating around the cultural sphere. Where did Churchward even get that name?
He appropriated the name Mu from an even earlier fringe researcher, Augustus Le Plongeon, who had used it in the 1880s in reference to...
Wait for it. Atlantis.
Atlantis. This illustrates a critical point. These mythological constructs are incredibly sticky and iterative. Atlantis, Mu, and Lemuria are constantly borrowing names, details, and geographical locations from each other.
All unified by that single powerful underlying theme.
Exactly. The theme being the need for a lost pre-cataclysmic civilization that explains why we feel we've lost some ancient wisdom today.
That's the core of pseudo-archaeology and occult belief here?
It is. As L. Sprague de Camp detailed in his 1954 classic Lost Continents, the reason the idea of a submerged ancient continent persists is that it fulfills that deep psychological need for a sublime hidden history. It provides an explanation for anomalies and fills the human desire for a dramatic, cataclysmic origin story.
It doesn't matter if it sank in the Indian Ocean, the Atlantic, or the Pacific.
The emotional purpose remains the same.
Once Lemuria was embedded in theosophy and popularized by authors like Churchward, it started showing up in diverse and, frankly, bizarre geographical and cultural locations. It stopped being a theory and became a cultural template. Let's start with the largest terrestrial landmass that Blavatsky claimed was a Lemurian remnant, Australia.
The Australian connection is fascinating and deeply problematic. Blavatsky made the specific assertion that Australia was an inland relic of Lemuria that had not fully subsided.
Right.
This led to her attempting to fit indigenous populations into her spiritual timeline.
And her claims were highly racist, suggesting a deeply flawed evolutionary sequence for the Aboriginal populations.
She claimed that Aboriginal Australians and Aboriginal Tasmanians, whom she identified as a separate group, were the remnants of the Lemurians, specifically a later degenerate branch of the third root race. In her system, their primitive state was explained as the result of crossbreeding with animals.
A concept which today we recognize as scientifically unfounded and just, abhorrently racist. Unfortunately, this idea, however distorted, found traction within the white Australian popular culture of the late 19th and early 20th centuries. It kept appearing in pseudo-histories and fiction written by colonial authors.
I did, and you have to ask why. Why would the white settlers be so attracted to a lost continent myth that connected them to a supposedly degenerate race?
It seems counterintuitive.
The appeal was twofold, reflecting deep colonial anxieties. The historical study of this period, particularly by Robert Dixon, suggests that the popularity of the lost races, trope like the Lemurians, reflected a profound cultural anxiety among colonial Australians.
What was the anxiety?
The anxiety was that when Englishness is lost, there is nothing to replace it. Without a grand, ancient European history in the land, there was a void.
So a lost, mystical land like Lemuria provided a dramatic, non-indigenous and prehistorical lineage for the continent itself, giving it depth and mystique without having to acknowledge or integrate indigenous history.
Exactly. They were attempting to manufacture a romantic, deep-time history for the land that didn't involve confronting the contemporary reality of colonialism, displacement, and violence against indigenous people. A.L. McCann attributed the use of the Lemuria trope by authors like Rosa Campbell Praed as an attempt to create a lineage for white settlers without having to confront the annihilation of indigenous people.
So we see this trope pop up repeatedly in the literature of the time.
Yes. The poet Bernard O'Dowd used it in his work to imbue the landscape with ancient significance. And the idea was central to novels, specifically George Firth Scott's The Last Lemurian, a Westralian romance where the lost civilization is hidden in Western Australia. John David Hennessy's An Australian Bush Track also uses the motif.
So it demonstrates how a scientific theory, through the filter of theosophy, became a convenient narrative tool for white settlers.
A tool for seeking to justify their presence and elevate their new home historical significance.
Now we move across the Pacific to where Lemuria is arguably most famous today, Mount Shasta in Northern California. The Lemurians didn't just leave a land remnant here, they went entirely underground.
They did, creating a spiritual hub that persists to this day. This is the dramatic relocation of the Lemurian survivors from the sunken continent into the mountain itself, establishing the highly influential North American Lemurian tradition.
And this started with an occult novel.
It started in 1894 with Frederick Spencer Oliver's occult novel, A Dweller on Two Planets. Oliver claimed that the survivors of the sunken continent had created an elaborate complex of tunnels and caves beneath Mount Shasta,
A hidden city.
a beautiful hidden city known as Tellus, City of Light.
And the vision he presented was one of incredible opulence and spiritual purity.
Oh, yes. Tellus was described as a technologically and spiritually advanced sanctuary, with fur-lined carpeted floors, walls studded with jewels, and incredible light sources. Furthermore, Oliver claimed that these Lemurians were not completely hidden. They could occasionally be seen walking the surface of Mount Shasta, easily recognizable in their characteristic white robes, radiating health and spiritual power.
That's a powerful image. A secret utopia accessible just by climbing a mountain. This fantastic seed was planted in American esoteric geography, and it was quickly fertilized by new religious movements.
It gained critical traction in 1931 when Harvey Spencer Lewis, who wrote under the pseudonym Wishar Spencer, published Lemuria, The Lost Continent of the Pacific. This book cemented Mount Shasta's role as the definitive repository for the surviving Lemurians, making it a powerful spiritual focal point.
And then the belief proliferated massively through a specific mystical movement, the I Am activity, led by Guy Warren Ballard.
Ballard is absolutely central. He claimed that while hiking on Mount Shasta in 1930, he was approached by a major mystical figure known as the Ascended Master Saint Germain. This master purportedly endowed Ballard with profound knowledge and wisdom about the hidden workings of the universe and the history of Lemuria and Atlantis. Ballard documented these experiences in his book Unveiled Mysteries, published under the alias Godfrey Ray King.
So the Lemurians beneath Talos are now linked to a specific active spiritual lineage known as the Ascended Masters.
Exactly. Through Ballard's teachings and his subsequent organization, the Saint Germain Foundation, the core of the I Am activity, the belief in Telos and the presence of the advanced, enlightened Lemurians beneath Mount Shasta became codified and institutionalized.
And this belief is far from a historical footnote. It is maintained by a whole host of religious and spiritual groups today, right?
Absolutely. It has become a core element of various syncretic New Age and esoteric movements. Groups like the Great White Brotherhood, the People to Freedom, the Summit Lighthouse, they all adopt, adapt, and continue the belief system surrounding Telos and the Lemurian masters.
And that has established a deep physical, cultural footprint on the mountain itself.
It has, in the form of annual gatherings and pilgrimages. It's a living tradition.
A vibrant, contemporary tradition.
Yes. Every year, members of these various religious groups make pilgrimages to Mount Shasta. The Saint Germain Foundation, for instance, hosts the annual I Am Come pageant. Similarly, groups gather for the annual Rainbow Gathering in August, all focused on the spiritual cleansing and high vibrational energy attributed to the mountain and the hidden city beneath it.
What's unique about the spiritual practices of these blended religions, they sound like they are pulling from everywhere.
They are highly syncretic, which means they blend and borrow selectively. They're a synthesis of various spiritual practices, Native American spirituality, Christian concepts, Buddhist ideas, even Taoist traditions, but they are often selective, excluding what they consider negative or low vibrational aspects.
Can you give us an example of that selective synthesis, the purified version?
A specific detail highlighted in our sources is that the Saint Germain Foundation, for example, emphasizes the risen Christ, but actively excludes the details of Jesus' crucifixion in their teachings.
Interesting.
They focus only on the aspects of spiritual triumph, ascension, and enlightenment, creating a clean, high-frequency spiritual lineage traced directly back to the supposedly enlightened Lemurians who escaped the cataclysm.
Finally, we have to acknowledge a critical parallel tradition in South Asia that became heavily intertwined with the Western concept of Lemuria.
The legendary sunken landmass known in Tamil literature as Kumari Kandam.
This link is a perfect illustration of what we call retroactive legitimacy, how a scientific hypothesis, even one later discarded by Western science, can be used to legitimize an ancient, purely cultural legend.
That's precisely the dynamic we see here. Kumari Kandam is a profoundly important mythological and political concept in ancient Tamil literature. It describes a great landmass that was ruled by the Pandyan kings of South India before being swallowed by the ocean.
So before the 19th century, this was a story of cultural memory and mythology. How did Lemuria suddenly attach itself to it?
Well, in the 20th century, particularly within the Tamil Renaissance and later Tamil nationalist movements, writers and scholars began associating the Western idea of Lemuria, the sunken continent in the Indian Ocean, with their ancient legend of Kumari Kandam.
So they saw this Western scientific theory and said, that's our story.
They did. Writers like Devanya Pavanar championed this association, positioning the combined concept as the ultimate cradle of civilization, specifically the origin point for the Tamil language and Dravidian culture.
So it shifted from being the origin of lemurs, or the source of Western occult knowledge, to becoming the mythological and purported scientific origin point for one of the world's most ancient linguistic traditions.
Exactly. It became an incredibly powerful political and cultural tool for defining ancestry and historical prestige. Our sources reference the ancient description provided by the Tamil commentator Adiyar Kanalar, who described Kumari Kandam's vast dimensions extending between the Parali River and the Kumari River in the Pandyan country before that land was completely subsumed by the sea.
This connection provided a precise geographical and historical anchor for a story of immense cultural loss, framed not just by myth, but suddenly by a Western scientific theory, even though that theory was obsolete.
It really demonstrates that the story of Lemuria is a powerful template. You can plug in whatever ancestral story you need, lemurs, esoteric wisdom, or the cradle of civilization, and the template works.
Because the catastrophic sinking gives the origin story drama, tragedy, and undeniable mystique.
So what does this all mean when we connect all these threads together? Lemuria is a powerful, almost perfect historical example of how a concept born out of pure scientific necessity can be completely divorced from its empirical base and reappropriated and sustained by popular imagination and mystical systems.
Long after the evidence, in this case plate tectonics, has definitively discarded it.
Exactly.
It is the ultimate intellectual chameleon, capable of shifting its meaning to fit any cultural need. It began as a highly specialized fix for a zoological distribution problem. It was then leveraged by prominent Darwinists like Haeckel to explain human evolution and solve the mystery of the missing link. And finally, it was sanctified by occultists like Blavatsky and her successors to explain hidden knowledge, spiritual ancestry, and the eventual downfall of mankind.
The key takeaway here and the core insight of this deep dive is that the enduring idea of a lost continent, whether it's Atlantis, Mu, or Lemuria, is fundamentally less about geology and far more about the deep, enduring human desire to place our present existence in a sublime, hidden, and cataclysmic past.
It grants history weight, meaning, and tragic romance. It gives the current world a sense that something incredible, something profound was lost, and that we are the inheritors of those hidden fragments.
We've seen Lemuria used by 19th century scientists to explain the migration of lemurs.
By a late 19th century occultist to define sequential human origins.
And by 20th century Tamil writers to define the cradle of civilization. This raises an important and compelling question for you. If you look closely at history, how many other seemingly factual beliefs start their lives in one field like sober observational science, but endure for centuries, sometimes millennia, because they satisfy a completely different, deeper cultural or spiritual need?
Think about that incredible intellectual journey, from Sclater's journal to the jeweled caves under Mount Shasta. What stands out to you about the sheer, undeniable power of a good origin story, even one that was definitively sunk by geology? That's something worth mulling over.